Good morning. This is Sean Murphy of SK Murphy. I'll be the MC for today's PATCA briefing on AI-driven electrical schematic analysis. PATCA is the Professional and Technical Consultants Association. Learn more at patca.org. Best way to get started is to join as an associate member for $50. You can contact me at skmurphy@skmurphy.com if you have questions. We are fortunate today to have Gilad Shapira, co-founder and CEO of CADY Solutions, as a speaker. Gilad co-founded CADY in August of 2020. The firm is headquartered in Tel Aviv. He holds a Master's of Science in Statistics and Data Science from Tel Aviv University. Prior to CADY, he worked on applying artificial intelligence and machine learning techniques to research and industrial problems. Gilad.
So thank you so much. Today I'll be showing you what CADY is all about. So as you said, we are based in Tel Aviv, and we serve many hardware companies around the world. Very different verticals, as you can see here. Automotive companies, medical devices, IoT, telecommunications, semiconductor, very different, but all have one thing in common. They develop very complex hardware. And where we fit in, or what we do for those companies, we offer them an automated design review layer to fit in right between the schematics and the layout. So currently, when designing a PCB, you know better than I do how frustrating it is to debug the schematic. It's not at all like software where you have automatic debuggers to do your work, or like to assist you and detect errors and give you warnings, and like co-pilots even give you best practices and offer you new connections, or like encode new lines. In schematic, you don't have that. You have your hands, your eyes, your peers, maybe DRC tools to assist you. And we provide you with that debugger that helps you. And now it became from debugger at first to full co-pilot today that fits in right between the schematic phase and the layout phase, and allows you to detect errors early. It provides you warnings. It gives you best practice recommendations. It enforces design rules that you have specifically in your company regarding naming conventions, or how to connect different kind of pins or components or whatnot. I'll give a lot of examples down the road, but the general idea here is to give hardware developers what software developers have for many years now, debuggers, or nowadays even you can call it a co-pilot. And the idea is that in order to use CADY, you don't need to trust CADY with your data or train CADY with your data. You just upload your design files. It's encrypted, and then it's analyzed, and it's completely erased from the system. We don't train on design files. We don't train on user data. It's not even saved in our servers. So bottom line, running CADY, and I'll show today how to run CADY, how it's done, what's required, but running it takes 5 minutes, and you have no risk of IP, and the result is error detection, warnings, best practices that can save you significant costs and accelerate your time to market. Because imagine, and that happens often, when you catch an error with CADY before layout and before bring up, and then saving a respin, or even saving a potential recall or repair on site for some things that are more subtle and would have passed the bring up. So that's the motivation for CADY in general. And I'd love to dive into how exactly it works and what exactly it can and cannot do. What is design review? What is design analysis from our perspective? Shall I continue or stop for questions? Just go ahead.
So we'll take questions in the chat as we go, and I will stir them
Perfect.
to you as they come.
Perfect. Perfect. Um, so just a second. So how does CADY work? There are two pillars of information that CADY relies on. First of all, the public information that comes from data sheets of components around the world. For CADY, a schematic is simply a puzzle of hundreds, thousands, sometimes tens of thousands different pieces. Each piece is a component. It could be the most simple capacitor or resistor or the most complex FPGA or microcontroller. And then, in order for Katie to understand if the puzzle is correct, meaning all components are connected according to, are connected correctly, let's say, there are two things to do. First of all, to check against the data sheet of the component. That's the first pillar. Then to check versus common knowledge or electrical engineering knowledge. That's the second one. The first pillar, the datasheet one, is something we've built. It took us a lot of time to collect millions of data sheets of components around the world from vendors like, it could be Vishay and Murata, and it could be NXP and Marvell, and then Qualcomm and Broadcom, etc. Some of them are confidential, so we had to sign NDAs and, you know, um, develop a very close relationship with the manufacturers and the vendors of those confidential data sheets or the confidential components to acquire the data sheets. But now we are in a position where we have access to 99.9% of data sheets out there, both public and confidential. So we understand how the manufacturer, how the vendor instructed the user, the engineer, to connect the component in the design. And that's something our AI datasheet parser reads from the datasheet and understands. Now, it saves the information into a database, and then, given that database, the database says that for a specific component, I'll show you a few examples later, but for a specific component, pin 2 should not be connected to ground. Then the schematic analysis agent, the second pillar or the second, let's say, AI module that we developed, it takes the database information, but it also takes knowledge it accumulated from thousands of designs that we worked with or that we analyzed. Now, again, we don't save the designs, we don't train on the designs, but we do have the metadata. What kind of components were used? Was the feedback of the agent correct or not correct? The report is something that our agent learns from, the interactive report that I'll show you later on. So the feedback of the engineers we work with from, NVIDIA and Zebra and John Deere and all the other customers that I showed you earlier, that information is accumulated so the agent knows not only how the component should be connected in terms of the datasheet, but also what's the common knowledge or common practice regarding that kind of component or in general. And then even if it doesn't say so in the datasheet, the system can still point out errors, warnings, best practices, or vice versa, not pointing out things even though the datasheet instructs. I'll give again examples down the road.
So
So
Gilad,
yes,
we've had a couple of detailed questions come in.
of course.
Let me start with the with uh both of them essentially ask about new parts. If I have a new part, how do I make sure you have it?
Great question. So I hope we'll have time to present a demo. In the application, in the agent, the output shows you which components were supported. And if one of the components datasheet is missing from the database, which is a rare situation, but it happens. It could happen, by the way, if it's your ASIC. So if it's your component, of course, we won't have access to the datasheet. We have access to datasheets of third-party vendors, public and confidential. Sometimes it's upon request, sometimes in advance, like in NXP and Marvell and Broadcom, etc. But if you're working in, I don't know, company X and you have an ASIC that you're developing, the only way for us to support it is for you to upload the datasheet, and you have in in the analysis report or the analysis output, you have indication which components lack datasheet, and then you can upload the datasheet to the
So
platform.
I can upload a data sheet
As
for
a
a
user,
component you
yes,
don't have it.
you can
Okay.
do that, and then it's segregated, encrypted, and our system can support it and then include it in the analysis once you rerun the files because we don't save them.
Okay. So there's a follow-on question, which is TI recently changed the specs for some op amps. So even if you've got what you think is the correct data sheet for a part, can I say use this new data sheet instead?
Yes. So first of all, yes. Second of all, as you can see here, we update our database of datasheets all the time, every 6 weeks. So, and it's done continuously and offline. So we collect datasheets from TI is maybe the most common one. We collect the datasheets and we update that collection all the time and rerun the datasheet parser every 6 weeks on the most up-to-date datasheet collection.
Can I get a URL or a copy of the data sheet for the part that you use to verify it?
So it's something that we can add if needed. The datasheet that the component we supported was matched to. So you know which datasheet it was and if it's the most up-to-date version, etc., etc.
So right now, how would I determine if you're using the most up-to-date version?
For now, you know that we do it every 6 weeks, and for special requests, we can add the link if needed. It's something that we have. It's just um, not in the native report as we do it every 6 weeks, anyways.
Okay. And then a question for which schematic systems can you import from or which do you work with? So what schematic capture tools do you support?
Yeah, so that's something I show in the demo as well. We support Siemens Expedition, Siemens Pads, um, um, Cadence ORCAD, Cadence HDL, Cadence Concept HDL, Altium Designer, Zuken, KiCad, Eagle. So I think the vast majority of ECAD are supported, and you follow our guide and export the netlist from it, and then you upload the netlist to the agent along with your BOM, which could be any format you choose or work with. Our agent is sophisticated enough to read your bill of materials without any format adjustments needed. And then it runs, it analyzes, and then it completely erases the netlist and BOM that you upload from the system and just keeps the report that was generated for them.
Do you have a slide on the tools you support?
I have a screen in the web, not here,
Okay.
but in the demo I show it in the website. Yes.
Okay. Um, so I got a question on uh, external loads for the schematic. Is it possible to use those to verify the proper behavior of the circuit?
What do you mean by external loads? I'm not sure if the one
So
that's
Carl, you
asked the
want to
question.
explain what you're trying to get at here?
Yeah, you have pins on your design that go out to the outside world.
Mm,
Oh, you
yes.
understand now?
Yeah, of course.
Okay. And so
That's a great
how
question.
do you add them in, or you just put them on the schematic as fake caps or what? Anyway,
That's a great question. So there are three different types of external loads for us. When you upload a netlist, usually it's either connected to the outside world via connectors, that communicate via, I don't know, HDMI, PCI Express, WhatsApp, whatever, and then the connector itself is enough for CADY to understand what's the connection to the outside world according to the protocol of that connector. That's the easy case, right? If you have a USB, a very simple board and a USB connector connected to the outside, we don't need you to tell us anything. The connector itself explains us what's the connection to the outside world. Then there are the cases where the board is connected to some kind of a system on module on the other side, like NVIDIA Jetson or an ARM module. Then we allow you to dictate to the system that a certain connector like J7 goes out to a SOM and then tell us the part number of that SOM, and we treat it as another component in the design. And the third situation is where the board is connected to another board, and then do another board. So it's a whole system. And then our system allows you to upload not one set of netlist and BOM files, but multiple sets of netlist and BOM files. We call it a multi-board. And then you can define to CADY which boards you uploaded, like board 1, 2, 3, 4, and the netlist and BOM for each one, and what's the connection between them. That J1 goes to J7, J2 goes to J8, and then CADY treats it as one giant board, and everything is interconnected, so it traverses between the boards and it checks things that are relevant to interconnections only, like if the net names between the both sides of each connector are the same or not the same, things like that. So it's something that we offer as well, yes.
Some companies create a superset spec for a part that allows them to do multiple sources for a part.
Yeah.
So in that case, I don't have necessarily a single data sheet I'm writing to, but I do have a spec I'm writing to. Is it possible to upload a spec like that or define a spec like that?
So the answer is that if it's a passive component, then we take in all cases, we take the first manufacturer part number that was chosen in the BOM, right? Even if there are 8, like in NVIDIA, for example, it's mandatory to have 8 alternatives for each component. We always take the first one in the BOM, the first manufacturer part number. However, first, our next step as CADY is to go from schematic analysis and expand it to BOM analysis as well, and then include all alternatives in the analysis of the schematic to feed the BOM in. We already started doing that in some sort of situations like BOM analysis that I'll show you later on, but that's one thing. The second thing is that if in the BOM you specify the spec of the passive component you want to work with, like it's I don't know, a 1% resistor, the package size is, I don't know, 0.402, it's, I don't know, 1 kilo, etc. Then the system will verify that the manufacturer part number you chose, the datasheet, actually corresponds to the spec you defined in the BOM itself. And for active components, yes, you can upload a dummy spec and say, okay, this is the spec that I want, but then it has to include the pinout and how you want the system to understand the connection of which connections of each pin you want to verify, what's the communication protocol of each pin. So it's a bit more complicated to create a dummy data sheet for active components, but for passive components, if the description just tells us what's the spec, then we even make sure that the datasheet of the manufacturer part number you chose actually corresponds to it.
Thank you. No more questions at this time.
Great. So CADY doesn't replace the engineer. It doesn't design schematics yet, and it doesn't replace the human in the loop, even if in the aspect of reviewing the schematic, right? Because in the end of the day, a lot of things that you do in a design review are connected to the intent of the designer, things that an outside, an external machine cannot understand just by getting the netlist and the BOM. However, it does serve as a very high ROI layer of defense, as it covers the most common errors that that are commonly made in a schematic. Some of them are simple, some of them more sophisticated, and it provides you warnings and best practice recommendations based on our community knowledge. We get a lot of feedback and new best practices that our users are using, and we allow other users to use. And we also enforce organizational rules when they are specific to an organization that decides to, I don't know, place a test point on each and every net in the design, or decides that a net name should not begin with a digit. Things like that, that are not mandatory but are specific to an organization. I'll give a few examples, what kind of things can CADY do. But it's always important to remember the context, which is that CADY is another layer of defense. It's not a replacement. It's assisting you. How does it assist? So, for example, a very annoying thing that can happen, and it's very easy to miss it in a manual design review, and a DRC will not catch it. Connecting an enable pin to ground or floating an exposed pad. Why is it so annoying and so easy to miss? On the other hand, because enable pins sometimes should be connected to ground, and exposed pads sometimes should be left floating. It really depends on the use case or on the component itself. In this case, this component specifically, the datasheet specifically says that the enable pin is active high and the exposed pad should be connected to ground. So in this case, the connections are wrong. Now, it can be even more frustrating when the lines are not in one page, but for example, if the enable pin was connected to a pull down and the connection to ground was on the other side, or you had an inductor in the way, or for bit, then you'd need to traverse the net from the enable pin to see in the end of the day if it was pulled high, pulled low, what happened. CADY does that for you. It understands from the datasheet that pin 1 is an enabled pin. It understands that it's an active high enabled pin. It understands that the exposed pad should be connected to ground. And then it traverses those pins in the netlist to their end connection, and it verifies that the enable wasn't connected to ground, even though it traverses via inductors and zero arm resistors and pull downs, etc. Same for the exposed pad. Moreover, as you can see here, there is a feedback pin. It doesn't say so in the datasheet of this component, but when you have a feedback pin, you see that the datasheet just says connect this pin to the external feedback divider. It doesn't say that the resistors, the feedback resistors, should be up to 1% tolerance. That's a best practice that CADY enforces for you. It doesn't use only, that's the two pillars I mentioned, not only the datasheet, but also common knowledge. Here's another example, pretty straightforward as well. As I said, sometimes the connections in a circuit are external loads, as you said, and sometimes it's via a connector that defines a communication protocol. Sometimes it's not a connector, but two components in the design. Sometimes it's a connector and a component that communicates in I2C, JTAG, PCI Express, HDMI, etc., etc. And one of the most common mistakes in schematic design, schematic capture, is to mix them up, the plus and the minus, the data and clock, etc., etc. And another common issue is to miss an ESD protection or termination or pull-up, like in I2C data, or to put two pull-ups in I2C because you placed in one page. Imagine that would be an I2C, so you see here the data like D minus, never mind. And let's say you put a pull-up and then you go to net label 41 on the other side, and now I forgot I put a pull-up already, and I do it again. So CADY takes the two components. It could be a connector and a component, or just two components, and it verifies that the connection is valid in terms of the protocol, meaning that the pins are not mixed up and that the correct termination slash pull up slash ESD protection is there. In this case, it's a USB protocol. The D plus and D minus are connected to an ESD protection, but and even though it goes via a resistor here, and it could go via an inductor or even a buffer, on the other side, CADY traverses the net and searches the other side. And the other side, after traversing those mid components in the way, the other side is mixed up. Net label 41 is connected to the P of another component, the USB plus, and it's a mix up. And CADY alerts is something that we see very, very often. So that's a second family of issues that CADY detects. The thing is that so okay, I'll go to the third one and then maybe I'll summarize so far. So the third family is a bit more like the communication is like how you connect two components. And the first one, the connection instruction, was about the peripheral connection of one component. Then there are things that relate to the to many components or like regional things across many components in the design. For example, voltage issues or current issues. So current issues we are not dealing with yet. We are now developing some, but voltage issues we most certainly do tackle, and that's more complex because that involves a lot of components and many times the voltage changes and then you have to calculate the voltage um, based on another component. So most of the times there will be a voltage regulator that takes an external voltage and regulate it, and CADY takes those regulators data sheets and calculates the output voltage based on the data sheet, either formula, like in this case, that's another, like in this case, R1 and R2 are controlling, and VREF are controlling the V out of this voltage regulator. And if it's fixed and not adjustable, it just just written in the datasheet what's that exact manufacturer part number output voltage. In this case, it's adjustable. So as you can see here in this example, R1 and R2 are placed in the formula. VREF is passed from the datasheet, and the software is able to calculate that this voltage is actually not 1.8 V, but 2.34. Now once there is such an error, there are a lot of things that can go wrong. First of all, the net name itself. The system alerts that the net name is inadequate. That's just a convention issue, but that could be very misleading. So the first thing the software will do is to alert the net name is wrong. Then it also goes and finds out if this kind of voltage is adequate to the components connected to it. And in most cases, if the net name is misleading, then the connections would be wrong. For example, here, a power pin connected to VDD1V8 works around VDD1V8, like in this case, this FPGA VDD ADC pin. And 2.34 is, of course, outside of the operating range. Sometimes it could be within the operating range, just not optimal, but in FPGAs and microcontrollers where the power domain is very narrow, like plus minus 10% of the voltage, the nominal voltage, then it's wrong. It could also breach capacitors or put capacitors in potential breach under the rating of, we let our users dictate what the rating factor they want to take for capacitors, but we catch a lot of places where the capacitors are in a potential breach situation or even a breach situation where the rated voltage is not adequate in terms vis-a-vis the or in comparison to the DC voltage connected to the capacitor. So that's in general. And of course, there is a lot of data beyond what I've shown you today. Beyond that, these examples that I showed you that CADY uses to perfect your design, to correct it and to perfect it. And I can share more examples in the demo, but let's see if we have time for that. If not, we have some videos on our website, and of course, we can I can send a video, or you can book a demo with me or my people to my employees to see more. But that was just a few examples to show you CADY is not another DRC, but something much, much beyond it. It's more like a co-pilot that analyzes your design and assists you in making sure you prevent respins, um, at least when it comes to schematic errors. In the future, in the near future, we will proceed to BOM analysis as well, as I said, both checking alternatives and then suggesting alternatives. If we say that the capacitor is about to be breached, we would also recommend a different capacitor to be used instead of it. And then it could be based on your BOM or PLM, or based on your vendors that you work with, and via API connections that we already have. We are integrated with Silicon Expert. So we have that data connection out there outside of the of the system, to marketplaces and such. And layout analysis as well is something that we plan to release beginning of 2027. Very similar to the schematic analysis. Again, assisting in verifying and analyzing and perfecting the layout before moving on to a bring up. The end goal is to design to be a design assistant, meaning when you design the schematic or the layout, CADY suggests design connections live, but it's never, even in the wildest dreams, CADY will not replace the engineers. It will always be there to assist them, just like we see, software developers enjoy so many, AI tools that assist them. That's the mission of CADY for hardware developers. That's it for today. This is the website. This is my email. Feel free to reach out to book a demo or to ask any question you might have. And of course, I'd be happy to answer your questions now.
Other questions for Gilad? Do folks want to stick around and take a look at the demo?
Could I just verbally ask a question?
Sure, go ahead.
Yeah, this is Jerry. If you purchase one or a package for a particular board, and then at some point later, in less than a year, if you release a new version that has improved features, do you get to use the new
Yes.
version to? Okay.
Yes. We are classic SaaS in that aspect. We don't charge, we don't segregate the versions. The version is the same version, um, and it's improved. It improves for all. Um, or you
So,
mean
Neil,
your board version? If you mean your board is
Yeah.
changing,
No. I think you've answered the question. I just
okay.
mean at some point, if you add new features, um, how will you handle that? If the feature is how do you will you have different
Just yeah,
pricing if you?
no, it's rolled out automatically to all of our customers, and then once you analyze again, the features automatically update for you. It's not like we charge per feature or something.
Okay. All right. Thank you.
I'll just add, by the way, if the board is changing, like you analyze the board and then in 3 months you analyze it again, even if the components change, you can still analyze it on the same slot. You don't need to open a new slot for each variation. You have a slot for your board, and as long as it's similar, like 70, 60, 70% of the active components are the same, then we trust you that it's the same board and you can run different variations, versions, revisions that you have for that board throughout the year. We even have a revision control track to help you see which revision you actually analyzed when, because we know when you use CADY, you normally change things in your schematic and then you want to analyze again after the changes. So, yeah.
Well, why don't we take 10 minutes for a demo?
Yeah, it could be even 5 actually. It's very, very simple. Let's see. Can you see my screen?
Yeah, it's the wrong thing. We have one more question. Neil, please verbalize your question. I'm not able to do it justice. I see you rapidly muting and unmuting. I'm not quite sure. No mic. Well, so my problem is he's answered that question to my perspective. So there must be some nuance that I'm um, missing. I'll put his email address again in the chat, and I would suggest that you email the question in the appropriate level of detail and let him
Yeah,
answer it offline.
no problem. So this is the system I told you about. Very simple. You create a slot, a board, let's say board one, board two. It could be a multi-board module, we call it, and then you can upload multiple boards and define the connections between them, as I told you before. Regarding the ECAD environments that we support that you asked about before, so as you can see here, these are all the environments, and when you click one of them, it takes you to a guide to show you how to export the relevant netlist formats. So Cadence, for example, you just create the native one. In Altium, you create a Protel 2 netlist, like that, netlist for product. That's it. And you upload it here. You create a board and you upload it here. Very, very simple. Now, as I told you, there are best practices that the system offer, and there are things that you can configure. For example, if you want the system to alert on a potential capacitor breach from 70% derating, meaning that the rated voltage after derating, after taking 70% or 30% off, the rated voltage, it exceeded by the DC voltage, then you can choose the actual derating factor here, either for all types of capacitors or to change it here. If you want to make sure all your components are operating in a certain range, you can change it here. And there are a lot of rules. It doesn't say so, for example, in the datasheet of a P-channel MOSFET that you need to connect a gate source resistor. But it's something that our users asked us to add. So we added it. And then another user asked us to add it for N-channel as well. So we added it as well. So that's how we add rules all the time. And if you have rules that you want to suggest, feel free. That's how you configure the parameters. And you run the analysis. Drag and drop your netlist, boom, that's it. After the analysis is complete, by the way, that's how you track revisions. You can add revisions and you can reanalyze the board again and again throughout the license period. Once the analysis is complete, you get an email that the report is ready. It often takes a few minutes. Sometimes for the first run, it could take a few hours, but not longer than that. And it all is done in the background. And you can view a report. Things you marked in the past for this board, for example, I marked in the past that this is an error that needs to be fixed because the system alerted on a capacitor that is 6.3 V rated voltage, but it's connected to 5 V. And I wrote to my colleague, Tal, replace, but he didn't. And I wrote him again, replace, and he didn't. So that's how I can collaborate with my colleagues and make sure they fix things, or collaborate with myself and just make sure I fixed what needed to be fixed. And if something I marked as skip, it means I live in peace with it and I don't want the system to alert each time that it happens, so it stays as skip. You go over the findings, and it could be voltage issues, connection issues, it could be BOM violations, it could be best practices, it could be supply chain issues or lead time or end of life or things like that based on silicon expert integration that I told you we have, redundancies like redundant pools that I told you about, things like that. I can mark them myself to fix or not. I go to my schematic environment, I fix it, and then I run the board again to see if it has been fixed. For example, these errors I haven't fixed since I marked it, so I need to go fix and then run again and see that they disappear. It's very important because If I fix them, some other could pop up, so I need to keep tracks on my findings. That's how a report looks like. It also shows you not only it shows you things regarding your circuit, like which nets the system detected as or defined as power nets based on the net name, based on the fact it's coming out of a voltage regulator. What's the voltage it calculated, and you can override it or assign voltage to nets that, for example, if it's a battery voltage, we won't be able to know what's the voltage unless you write it on the net name or you write it here. We also map capacitors, and we let you know what's the actual derating on each and every capacitor you have in your circuit. Things like that. And as I told you, if a component is missing in terms of a data sheet, so the system CADY doesn't have a data sheet for that component, you can upload a data sheet and then it will be supported, and you can rerun the analysis, and then the component will be supported. So that's how you know what's been covered in the analysis and what not. That's the system. It's very easy to use. I told you it would take less than 10 minutes to show it. Do you have any questions about the demo or in general? We have 1 minute extra for additional questions if you have. I
No,
see
this
the
is
chat is like exploding, but I let
no,
you
no, no.
go over it.
I'm just putting your contact information, a summary of the pricing and
Perfect.
licensing stuff. Um,
Perfect.
so any final questions for Gilad before we break? All right. Well, this has been very educational. It's a very interesting kind of modality where it's almost like a batch program. Um, and you've thought about a lot of stuff. You've been in operation. You've started in August of 2018, and clearly been at it a while.
2020.
2020, sorry, 2020.
Yeah. Yeah, it's
Um,
been a while. It took time, but yeah, it takes time to develop such a tool, but we love serving our customers, and we keep on improving always from their feedback. So feel free.
and we'll post a copy of the deck. I
Mhm.
want to thank everybody for coming, and I think we'll break here then. Thanks, everyone.
Thank you. Have a great day.
Yes. Bye.
Bye bye.